Dear students, today I want to revise the topic electric potential. We know the simple concept. Electric potential is nothing but the work done to take a unit charge, say Q0, from infinity to that particular point. So we can mathematically express it as V is equal to W by Q0. And we are treating that potential as a scalar quantity and are expressed in volt or joules per coulomb and got a dimension of ml square t raised to minus 3 ampere raised to minus 1. We can just go through the simple equations in relation to the potential. The potential due to a point charge at a separation r we can find as V is equal to 1 by 4 pi epsilon 0 into Q by R. The potential at a point due to the collection of charges, it is a scalar quantity, so have to take the algebraic sum of individual contributions. So we have to apply the principle of superposition. So we can easily say 1 by 4 pi epsilon 0 sigma Qi by Ri. Then we can link with what is the equation for potential for a continuous charge. And suppose that a small element got a charge of dq and is at a separation r from the point, then we can say as 1 by 4 pi epsilon 0 integral dq by r. But keep in mind, for the continuous charge distribution, if it is a line of charge, then you have to apply the linear charge density lambda, and hence we can replace as dq by lambda dl. If it is a plain sheet or a plain lamina of charge, then you have to replace dq by lambda sigma ds. But if it is a volume charge distribution, it is rho dv by r. And see the case. And here we are plotting the potential variation with the separation for a combination of charges minus q plus q. At a particular point, their contribution becomes 0, that is labeled here. We should know what you mean by the potential difference between the 2 points. Between the points A and B are labeled as VB minus VA. That is nothing but the work done to move it from A to B by Q0. In integral form, we can write as equal to negative of integral b to a of E dot dA. That is a very important relation. But in order to find the potential at a point A, suppose we are taking it from infinity, then you have to take B as infinity. So minus integral infinity to A E dot dA. So we can again go through some important situations. Here the electric potential due to a charged ring. So the ring and a point P under consideration at a separation x. The potential at that point P is nothing but a good concept as 1 by 4 pi epsilon 0 q division by that r is nothing but equal to root of r square, the radius square plus x square. Look the two very important cases. What is the contribution to a conducting sphere or a shell? We have to find what is the potential at a point on outside, at the surface, and also at any point inside. So at any point outside, we have to consider the whole charge is concentrated at the center at a separation r, and hence the formula become 1 by 4 pi epsilon 0 q by r. But on the surface, you have to replace that small r by capital R. But keep in mind the very important concept, at any point inside the electric field is 0. That means, again the electric field is the negative gradient of potential. Therefore, dV by dr equal to 0. That means V is equal to a constant. So it takes the same value on its surface. So at any point inside, we take the value as V surface is equal to 1 by 4 pi epsilon 0 Q division by R. Look the graph variation. From R equal to 0 to capital R, it got the constant value, the maximum value, it got the same value on its surface, and then it is inversely proportional to R. But the case is entirely different for a non-conducting sphere. The similar concept as thereof that conducting sphere or shell for the points well outside and on its surface. But at a particular point inside, it is a totally different one. And keep in mind that at any point inside V3, take the value equal to 1 by 4 pi epsilon 0 Q by 2R cube into 3R square minus R square. But if you find the concept as a small r equal to capital R, you get the value, the same concept as that of V2. But at any point on its center, that means a small r becomes 0, you get the value as 3 by 2 times that on its surface. Look the variation. It's a very important concept. At a particular point that is small r equal to capital R, that value is, you can compare it with on its center. On its center it is 3 by 2 times of that on its surface. So you look the segment and it makes an angle alpha with respect to center. The potential at the center is given as 1 by 4 pi epsilon 0 lambda alpha. So these relations are very, very important to solve the problems based on electric potential. Look again some important concept. The potential due to a line of charge. So here a point P at a perpendicular separation y from this one, and here it is a finite length L, and there we can derive it to be V is equal to 1 by 4 pi epsilon 0 lambda. The lambda is the linear density, logarithm L by 2 plus root L square by 4 plus y square by minus L by 2 plus root L square by 4 plus y square. But from A to B, nearby distances. So here A and B are two nearby places, and we are moving the charge from A to B. So potential at the point A minus VB is given as minus lambda by 2 pi epsilon 0 log. Look the next case, the electric potential due to an electric dipole at a particular point P with an orientation r theta. So the potential can be derived to be equal to 1 by 4 pi epsilon 0 into P cos theta division by r square minus L square cos square theta. So for a short dipole, we can assume it to be the length of the dipole is very much less compared to the separation, and there we can write is equal to 1 by 4 pi epsilon 0 into P cos theta division by r square. And keep in mind, when theta equal to 90 degree, there cos 90 becomes 0, and then keep in mind at any point on the equatorial line the potential is 0, and that line can be treated as an equipotential surface. Next, the very, very important concept, and based on our JEE main entrance examination, the dipole interaction. Look if along the axial line they are parallel but perpendicular, what is the relation for the interactive force between the dipoles and the potential energy? And here the two dipoles are aligned like this with their centers are separated by a distance of r apart, and that each one got the dipole moments of P1 and P2. Then the force of interaction can be written as is equal to, they are attractive in nature because of the negative sign, so minus 1 by 4 pi epsilon 0 6 P1 P2 by r raised to 4. And look their potential energy as 1 by 4 pi epsilon 0 2 P1 P2 by r cube. For keep in mind the conservative forces, the force can be written as minus du by dr. And here the force of interaction, when they are aligned like this one, parallel, and they are with a repulsive force, are given by F is equal to 1 by 4 pi epsilon 0 3 P1 P2 by R raised to 4, and their corresponding potential energy is 1 by 4 pi epsilon 0 P1 P2 by R cube. But they are perpendicular to that one. Then keep in mind there is a rotatory concept is there, and they are exerted with the force of F is equal to 1 by 4 pi epsilon 0 3 P1 P2 by R raised to 4, and keep in mind they are perpendicular to that R, that is the direction of force, and the potential energy is 0. Then we can move to equipotential surface. The very important, based on our entrance exams, a surface on which the electric potential is the same everywhere. And keep in mind, higher the density of electric potential lines, larger the field strength. And keep in mind, if you just take a point charge, near to that point charge, the electric field strength is larger, and hence the equipotential surfaces are close to it. The close to the charge, it is very important. The direction of electric field is perpendicular to the equipotential surfaces or lines. For a uniform field, that equipotential surfaces are a family of plane perpendicular to the field lines. Look the different equipotential surfaces for different configurations, and keep in mind that red ink represents the electric field, and that black one represents the equipotential surface curves for a point charge, an electric dipole, two equal charges, and for a uniform field. It is very important one. And there is another relation between the electric field and the potential. The electric field is nothing but the negative gradient of potential. And keep in mind the vector concept, electric field we can write as EXI plus EYJ plus EZK, and is nothing but equal to minus dou V by dou XI minus dou V by dou J minus dou V by dou ZK. It is a very important concept. See, we can move to some problematic situations. Two charges, Q1 equal to 1 microcoulomb, Q2 equal to minus 2 microcoulomb, and Q3 equal to minus 1 microcoulomb are placed at A, B and C. Find the potential of the system of three charges at P1 minus 2 minus 1. So the position vector for the P point we can write as I minus 2j minus k. Then at first we can find the position vector of the first particle with respect to this point. So that is Rp minus R1. It is a very important concept. Then we can find what is Rp minus R2 and Rp minus R3. See, by knowing that position vectors, then you can easily find the potential at the point P due to the first one, that is equal to 1 by 4 pi epsilon 0 into Q1 division by Rp minus R1. So you can directly substitute the values. And similarly Vp2, it is 1 by 4 pi epsilon 0 Q2 division by Rp minus R2. That is equal to 9 into 10 raised to 9. And you can just substitute that Q2 division by the separation in magnitude. Similarly, we can find Vp3, and by the application of principle of superposition, here the potential is a scalar quantity. You have to add the individual contributions. See, find the work done by an external agent in slowly shifting a charge Q equal to 1 microcoulomb in the electric field E equal to 10 raised to 3 I volt per meter from the point P1 to 2 Q34. And we know the work done by the external agent against the electric field we can easily find as equal to minus Q into integral 1 to 3 Well, on the x-axis here the electric field, so the work is done on that one, so have to take us 1 into 3, 1 to, well, x is equal to 1 to 3 E dot dl. So here the electric field is along y, so ei into that xy plane as dxi plus dyj, then you integrate, you get the answer 2 into 10 raised to minus 3 joule, a good concept. The next one, for identical point charges, Q are placed at 4 corners of a square of side A. Find out the potential energy of the charge system. And keep in mind, while calculating the potential energy of different charge configurations, how many pairs are there? So we can easily find this concept, and keep in mind, you know the potential energy. Because of the two charge system Q1 and Q2, we can write as K into Q1 Q2 division by their separation. But here the 4 charge contributions are. So the different pairs responsible for the potential energy we can easily find to be equal to, if n number of charges are there, we can write it to be equal to n into n minus 1 by 2. So that is equal to here 4 into 4 minus 1, 3 by 2, 12 by 2, 6 in number. So 6 contributions are there between 1 and 2, 2 and 3, 3 and 4, 4 and 1, and then between 1 and 3 and 4 and 2. So we can just find their contributions, you know, the potential energy between the two charges with the separation RR, K into K1, K2 division by R. So you can find the value. Next question, a total charge capital Q is given to 2 concentric shells so that their surface charge densities are equal. Then what is the potential at their common center? So it is given that Q surface charge density to 2 concentric circles, say they are represented as charges are QA and QB, then capital Q is QA plus QB. So surface charge densities are equal. So we can write QA as equal to sigma into 4 pi a square and QB as sigma into 4 by b square. So we get the value for sigma. But we know the potential at the point that is equal to due to A plus due to B. So due to A we can write the point as sigma by epsilon 0 into A and plus sigma by epsilon 0 into B. So you get the answer. So if you go through thoroughly the theory part, then you can do the problems so carefully. Thank you. God bless you. Take care.